Some of the most complex questions in science and engineering, we're talking everything from designing a jet engine to predicting how a bridge will behave under stress, are solved using a surprisingly intuitive idea. It's an idea that connects the ancient world of artillery to the absolute cutting edge of modern technology. It's a weird question, right? I mean, one is about brute force trajectories, and the other is all about precision aerodynamics. But as we're about to find out, the logic connecting them is actually the key to solving a whole class of incredibly important problems. So, to really get our heads around this, we need to start with a simple but really powerful analogy. It's the whole basis for a technique that they call the shooting method. Okay, so picture this. You're an artillery officer. You know exactly where your cannon is, that's your starting point, and you also know exactly where your target is, that's your end point. The big mystery is the path the cannonball needs to take to get from point A to point B. The only thing you don't know is that one crucial detail, the precise angle to aim the cannon. This is the heart of our problem. So, what do? Well, you make an educated guess. You just pick an angle and you fire. Then you watch where the cannonball lands. Let's say you overshot it. Okay, no problem. Naturally, you're going to lower the angle a little bit. You fire again. This time you're closer, but maybe you undershot it. So you adjust again. And again, you're refining your aim with every single shot until, bang, bullseye. This whole process of guess and correct, that's the essence of the shooting method. All right, let's take that analogy now and see how it builds into the more formal mathematical concept we're here to understand. We're kind of shifting from a physical problem to a mathematical one. In the language of math and physics, this whole thing is called a boundary value problem, or BVP for short. That fancy term, differential equation, that's just describing the physics of the cannonball's flight. You know, how gravity and air resistance mess with its path. And the boundaries? Well, those are simply your known start and end points, the cannon and the target. A BVP gives you the conditions at the very edges of your problem, and then asks you to figure out everything that happens in between. This brings up a really important distinction. Because, you see, the kind of problem you're trying to solve changes completely depending on what you know right at the very start. So this slide here really breaks it all down. On the left, we've got an initial value problem. This is where you know the cannon's position and its starting angle. Your job is to calculate where it's going to land. But on the right, in a boundary value problem, you know the start and the endpoints. Your job is to find the initial angle that connects them. It's a subtle difference, but it's absolutely crucial. One is about predicting an outcome, and the other is about finding the specific path to a destination you already know. Okay, so this is a neat mathematical concept for sure. But why does it matter? Let's take a look at where these problems actually show up in the real world. And believe me, this framework is absolutely fundamental. It's working behind the scenes in technologies you use every single day. I mean, think about the stress on a bridge. You know the boundary conditions, it's fixed to the ground on both ends. You apply a load in the middle, and you solve for the deformation in between. That's a BVP. Or what about the airflow over an airplane wing? You know the air velocity way far away from the wing, and you know the air has to stick to the wing's surface, so you solve for the flow and the lift in between. Heat transfer, electromagnetics, even acoustics, they all rely on this same idea: define the boundaries and solve for what's happening inside them. And check this out. This is a perfect example of what a boundary looks like in a real engineering model. Here, inside this COMSOL simulation software, an engineer has defined what's called a symmetry plane. They're basically telling the computer, hey, I know the behavior on this side is just going to be a mirror image of the other side. By setting this condition, this boundary, they can simplify a massive problem, which saves a ton of computation time while still giving them an accurate answer. And get this, even unbelievably complex systems are often built from simpler, fundamental models just like this mass spring damper. You just define its boundary conditions, like, say, one end is fixed to a wall, and that lets you analyze how it responds to different forces. Engineers build up from these basic BVPs to simulate pretty much everything, from a car's suspension system to the vibrations in a skyscraper. So, if engineers are using BVPs for everything, how do they actually go about solving them? Well, for that, let's get back to our cannon. This quote from the source material just perfectly captures the elegance of this whole idea. The core strategy, even for these mind-bendingly complex problems, is basically the same as our artillery officers. You guess, you check, and you adjust. You just keep shooting solutions until you find the one that hits your target condition. But of course, it's one thing to adjust the angle of a cannon. It's a completely different ballgame when your shot is governed by the laws of fluid dynamics or even quantum mechanics. And this is what finding the right shot can look like under the hood. Whoa, this is just a page from a research paper on solving these problems. Now, we don't need to understand the specifics here, but the visual alone tells a powerful story. The simple, intuitive idea of shooting is powered by some seriously heavy-duty mathematics.
And this is exactly why we have specialized tools. Software like COMSOL Multiphysics basically automates this incredibly complex shooting method. It lets engineers define the geometry and the boundary conditions, the start and end points, and then the software just rips through all the complex iterations to find the one solution that hits the target.
Okay, so let's just step back for a second and pull all of these ideas together. What's the main takeaway here? We've seen how a simple, centuries-old analogy for firing a cannon actually provides the intuitive foundation for some of the most advanced simulation technology we have today. It's pretty amazing. So the crucial point is this. Boundary value problems are absolutely essential whenever you know the constraints at the edges of your problem. It doesn't matter if it's the two ends of a bridge, the surface of a wing, or the start and end of a time interval. If you can define the boundaries, you have this incredibly powerful method for figuring out all the complex behavior that happens in between. And that kind of leaves us with a fascinating final thought. We're getting better and better at defining the boundaries of our problems and just letting computers solve what's inside. But as we do that, it forces us to ask a much bigger question. In our quest to model everything, what boundaries will always remain fundamentally unknowable?